Hi students, in this video we will study distance vector routing algorithm. This is working based on the standard Bellman-Ford equation. That is a standard equation in the dynamic programming scenario. Then let us take an example like this. D of x, y, x is suffix, d of x, y is equal to, what does it mean is, we need to find the distance to travel from x to y, where x is a node, y is another node. So the distance to reach to y from x is equal to minimum cost of c of xv plus v to y, distance v to y, xv, vy, where v is the neighbor of x. And minimum of these two, there will be a set of neighbors for x, and from all those set of neighbors there will be a path to the final destination also. So x to y means x is a source node, y is the final destination. To reach from x to y, there will be a neighbor to x. There will be multiple neighbors, and for every neighbor we calculate the cost of x comma v. Then it is added with the cost of v to y. Y is the final destination and v is the intermediate node. So the cost from neighbor v to destination is added to the cost to the neighbor. And minimum of all these set of neighbors is computed, and that will be updated in the table of d of x comma y, where d of x of y represents the distance to reach to node y from x. Hi students, in this video we will study distance vector routing algorithm, and the distance vector routing algorithm is working based on Bellman-Ford equation. And the Bellman-Ford equation is a standard equation used in the dynamic programming. And here it is given the same graph we explained for the link state algorithm. And the important equation, Bellman-Ford equation, according to the Bellman-Ford equation, suppose we need to find the distance from u to z. Then we consider all the neighbors of u to v, u to x, and u to w. Then from w to the final destination, from x to the final destination, from w to the final destination, it is added. So c of uv plus distance of v to z. Similarly, cost of u to x plus distance of x to z. Since we have three different neighbors to u, three different entries are there in the set, and minimum among the set is chosen. So cost of u to v is 2 plus v to z. V to z can be computed by 2 plus 1 plus 2. That is u to x to y 1, y to z 2. So 2 plus 1 plus 2 equal to 5. That is the cost of v to z. Then next is u to x is 1. Then x to z is 1, x to y 1 plus y to z is 2. So 1 plus 2 is 3. Then cost of u to w is, it's a direct neighbor, so it is 5 plus. Then w to z, w to z, there is a minimum cost path w to y, y to z. So 1 plus 2. W to y 1, y to z 2, 1 plus 2, 3. That is added to cost of UW. So UW plus WZ. So we get the minimum among these three is 4. So that is the table value to reach from U to Z. Here D of XY always represents the cost from X to Y. and the routing table maintained at router X, and d of x is equal to d of x to y, means from x to every other node where y belongs to n. So in the set of n nodes other than x to every other node. That is the meaning of d of x, y. Then node x knows the cost to each of its neighbor. That is represented as c of x, v. And node x maintains its neighbor's distance vector also. For each neighbor, Vx maintains a distance vector V. The key idea of the distance vector algorithm is it is d of xy is equal to minimum of cost of x to v and from v to y. And for every node y belongs to n. The key idea is it is updating the distance vector table time to time. And each node send its distance vector information to its neighbor periodically. When x receives a new distance vector estimate from its neighbor, it updates its own distance vector using the Bellman-Ford equation, and equation is given. This is what the core idea. So the distance vector algorithm is an iterative process and it is asynchronous, and at each local iteration it is performing the distance vector updation, and the cause of this updation may be a link cost change or a distance vector update message from its neighbor, etc. Or it may be periodically updating. Then the updation is done at each node. So it is known as a distributed algorithm. And when a neighbor changes its information, then it will update the new information to every neighbor of it. So the algorithm is working in a loop infinitely forever, and it waits for a cost change or a message from its neighbor. Then it recomputes the distance vector table, and this updated table is notified to all its neighbors. Here example is solved for the distance vector, and the graph is shown here. Only 3 nodes and 3 edges are there. The table is easy to create because we have only 3 nodes and 3 entries will be there, or 3 routing tables will be there at node X, at node Y, and at node Z. And in its row and column, it is filled with all its neighbors. So X have 2 neighbors, Y and Z. So X, Y, Z is repeated in the row and in the column. And if there is a path from X to Y, it will be filled. That is a value 2 in the first row of the node X table. From X to Z, there is a path 7 with the cost 7. Then from X to X, always it will be 0. Same node to its own link, there is no cost, so it is filled with 0. Then from Y to X, then Y to Y, then Y to Z. All are infinity because it is the initial table value. The table at node X will know the information of X only. And node Y is filled with its neighbors. So Y to X is 2, Y to Y is 0, Y to Z is 1. Similarly, for the node Z, from Z to X, 7 is the cost. From Z to Y, 1 is the cost. Then Z to Z, 0 is the cost. Then after a while, suppose we are thinking like this, the node X is getting changed. So node X is changing its table by collecting its neighbors vector table, distance vector table. That is what the arrow from y to x. X updates with the information from y and z. Y update the information from x and z. And z update the information from x and y. So here we are updating the routing table at node x. So it is collecting the information from node y and node z. Node y have second row filled with its value, and node z is its last row filled with its value. So the cost from x to y can be recomputed by the equation, Bellman-Ford equation. We need to replace x to y. D of x to y is the minimum cost of x to y plus y to y, because there is no intermediate node. So y itself is represented as y to y. X to y, y to y. Y to y is 0. X to y is 2. So 2 plus 0 is 2. Then next is distance from x to the neighbor is z. So x to y is computed. Next is x to z, z to y is another path. That is from x to y we can compute like this: x to z, z to y. So two different paths are there. So c of x to z is 7 and z to y is 1. 7 plus 1 is 8. Minimum out of these two is 2. So it is updating with the value 2. In this fashion, every other nodes are updated. So how this 3 is updated here? From x to z we have x to y, y to z. Then another path is x to z, z to z. So x to y cost is 2 and y to z is 1. 2 plus 1. Then x to z is 7, z to z is 0. So 7 plus 0, 7. Minimum is 3. So it is updated with 3. Similarly, every other nodes are getting updated. This is what the idea of distance vector table or distance vector routing algorithm. The algorithm is like this. The initialization part is similar to that of the linked state. D of xy is equal to the cost of x comma y for all destination nodes y in n. N is the set of all nodes and y is the node which we are considering now. D of x to y is c of x to y if it is a neighbor. Otherwise, it will be filled with infinity. For each neighbor w, send the distance vector d of x. Once the d of x is filled, it will send the updated table to every other neighbor. So this will be repeated forever in a loop, and this will be updated when the link cost of some neighbor nodes changes or it gets a new distance vector table from its neighbor. And the updation is with the help of Bellman-Ford equation, that is d of xy is equal to minimum of cost to x to y plus v to y. This is repeatedly executed forever. This is what the distance vector routing algorithm.